this work, the reactor was modeled using coupled mass and energy balances. The model includes substrate concentration, which represents the pollutant level, biomass concentration, which represents microorganisms, dissolved oxygen, and reactor temperature. To describe microbial growth, monod kinetics used together with decay effects, oxygen limitation, and temperature-dependent reaction rates. So after developing a mathematical model, the system is simulated in MATLAB to study startup behavior and disturbance response. Then an optimization problem was formulated to find the best operating conditions by balancing the pollutant removal, energy use, and reactor size. Now move on to the actual thing that we did. So this is the code that we ran. These were the results. So I'm now coming to explain the results of the code. So we have dynamic modeling optimization of a wastewater CSTR. The time used was 20.83 hours. The normal steady state effluent substrate was 11.71 milligrams. The temperature that it took place was 21.79 degrees Celsius. And the normal steady state for biomass was 259.18 milligrams. Right. Was 289.16 milligrams. So the purpose of the results section actually is to show 4 things. First, how the reactor behaves from startup to steady state, and also second, how it responds to the disturbances. Third, which parameters influence the reactor the most, and finally, how optimization improves reactor operation. So I'll begin with the tables. I'll actually begin with the tables showing the command window before I come to this ones. Okay, let me just do something small with the scenario summary table. So the scenario summary table, it's actually a table that shows us 4 things: the scenarios, the peak effluent, the minimum biomass, and then the minimum DO. And DO means dissolved oxygen. Yes, it is important numerically, but it shows that the optimizer, which is F main con, which I'll explain that very soon, improve the objective function step by step while reducing constraint violation. So when feasibility approaches 0, which we have over here, so when it approaches 0, the first order optimality increases. Sorry, it becomes very small instead. It becomes very small. As the more it approaches 0, the more it becomes very, very small. It means that the optimizer has converged with it properly. So this table confirms that the final optimal solution was found systematically and not by guessing. And then we have a table over here to the nominal versus optimized table. So this table gives the actual numerical values of effluent substrate, removal efficiency, biomass, dissolved oxygen, temperature, residence time, and power, total power in kilowatts. Now this table is important because it shows clearly whether the optimization produced a better engineering outcome. Now we move to the graphs. Yes, it is important numerically, but it shows that the optimizer, which is F main con, which I'll explain that very soon, improve the objective function step by step while reducing constraint violation. So when feasibility approaches 0, which we have over here, so when it approaches 0, the first order optimality increases. Sorry, it becomes very small instead. It becomes very small. As the more it approaches 0, the more it becomes very, very small. It means that the optimizer has converged with it properly. So this table confirms that the final optimal solution was found systematically and not by guessing. And then we have a table over here to the nominal versus optimized table. So this table gives the actual numerical values of influent substrate, removal efficiency, biomass, dissolved oxygen, temperature, residence time, and power, total power in kilowatts. Now this table is important because it shows clearly whether the optimization produced it shows whether the optimization produced a better engineering outcome. Now we move to the graphs. Yes, let's move to the graphs. Now talking about the graphs, we start with figure 1, which is the startup dynamics towards the steady state operating point. Now this graph shows how the reactor moves from initial non-steady state to from initial non-steady state condition to a steady operating point. Now the substrate concentration decreases with time over here, which means that the microorganisms are removing the pollutants. Now the biomass concentration increases at first. This one increases at first, which shows microbial growth. Then the level goes of decay, and then washout comes into balance over here. Where you have the balance over here. Now about dissolved oxygen, it adjusts until the oxygen transfer and oxygen consumption balance each other. You have the temperature over here also, and the value approaches a stable value because of the feed temperature, the reaction heat, and the heat exchange. So this figure tells us that the reaction model is dynamically stable and physically meaningful. Let's go to the next one. Next one here, figure 2. So figure 2 is a disturbance comparison plot. Now this top part over here shows the disturbance inputs mainly influence substrate concentration and flow rate. Now the bottom part shows the reactor response in terms of the effluent substrate and dissolved oxygen, which is also over here. When the effluent pollutant concentration rises, the effluent substrate also rises also rises temporarily, which means treatment performance is weakened for a short period of time. Now when flow rate over here increases, and the flow rate over here increases, the residence time also decreases. So when flow rate increases, the residence time also increases. Sorry, the residence time rather decreases. Sorry, it decreases. And so whatever spends less time in the reactor and treatment now becomes more difficult. Now if oxygen fails, if dissolved oxygen over here fails, which is over here, the minimum, if it goes below this, it fails. You find out that the treatment becomes means that the biological demand is high and the aeration may be insufficient. The aeration may be insufficient. So this graph helps us to judge how robust the reactor is under process shock. Quickly, let's move on to the third slide, the third graph, sorry, which is the state comparison under all scenarios. So comparing the state under all scenarios. And so this graph shows substrate, biomass, dissolved oxygen, and temperature together for each, all this for together for each disturbance case. Now it gives more complete picture of a reactor behavior. For example, if biomass drops during a hydraulic surge, that suggests washout rates. Now, if oxygen drops too low, that indicates oxygen limitation, and if all variables return towards their steady region after the disturbance, then the reactor has very good recovery behavior. So the graph is useful for showing not just the disturbance effects but also the system's resilience. Now moving on to the fourth one, which is the sensitivity analysis. The sensitivity analysis. Analysis plot, and this graph visually supports the sensitivity summary table. So that the larger the bar, you will find out that it is directly proportional to the importance of that parameter. So this figure helps us to see immediately which parameters dominate effluent quality and removal. So in practical terms, it tells us which variables or coefficients deserve the most attention in reactor design and process control. Now the fifth graph is the normal versus optimized CSTR performance, and we saw this earlier here, over here, the normal versus optimized CSTR performance. Now here we compare the original operating condition with the optimized one using using Yes, using quantities such as effluent substrates, the removal, the biomass, the dissolved oxygen, the residence time, and then the power. So the main purpose of the graph is to show whether optimization improves the trade-off between the treatment quality and the operating cost. Now, a successful optimized result usually means lower effluent pollution, better or maintained removal performance, and acceptable energy use. Acceptable energy use. Now to the safe graph. Now the safe graph is the objective contour plot. This shows how the objective function changes with flow rate and reactor volume. Now around the optimum. Now the mark point over here is the operating point over here is the operating point selected by the optimizer. Now, if you move away from that point, the objective becomes worse. And so this plot is important because it shows the trade-off between the reactor size and the hydraulic loading. And it is also indicating whether the optimum is sharp or is broad. Whether it is sharp or is broad. Now let's look at the final graph, the same in the final graph, which is a complex one. It is a three-dimensional graph, actually. A three-dimensional graph. Now, it is the effluent surface plot, and it shows how the effluent substrate changes with jacket temperature and aeration coefficient. Now, lower values on the surface mean better treatment. Now, this graph also explains why the optimizer chose a particular temperature and aeration level. It also shows that increasing aeration or temperature may improve performance only up to a point, which is after which the benefit becomes what smaller. So in summary, all the tables and graphs together show that the reactor reaches a stable state, it responds predictably to disturbances, and is strongly influenced by key biological and oxidative transfer parameters, and can be operated more effectively using optimization. Now, the overall engineering message is that dynamic modeling allows us to understand the reactor behavior, while optimization helps us to choose better operating conditions rather than relying on trial and error. Thank you.